Alright, so before we jump into Chapter 4, what I'd like to do is do a quick summary of the main definitions and theorems that we have so far, just to kind of prep us for what's going to be coming in the end of, or for most of what Chapter 4 is going to be looking at. In the applications that we look at in Chapter 4, kind of our big idea is to use theorems about the derivative in order to help us determine the behavior of the graph. And so a couple of big ideas that you need to remember from the previous chapters is our definition of continuity, that if we can prove the following three conditions, that the function exists at c, the limit as x approaches c on the function exists, which means the left equals the right limit, and the limit is the same as the function value, then we know the function is continuous at c. Our second big definition that's important to recall is our definition of differentiability, which is that first you have to make sure the function is continuous at c, and if it is continuous, then you move on to check whether or not it's smooth at c, that there's no cusp or vertical tangents, which means that our derivative f prime of c exists. Now there are several options in order to determine that the derivative exists at c. And what we can do is we can actually find a formula for f prime of c and then examine it for the domain. And if c is not in the domain, then of course it would not exist. And if c is in the domain, it would. If we had a piecewise function, which had a left and a right derivative, we would take the limit as x approaches c from the left on the derivative function. So you would take the left derivative and see if it's the same as the right derivative as x approaches c. You could also, the longer way, which we will hopefully not have to do on the actual AP, is we pretty much look at the quotient definition of the derivative using limits, and provided that this limit exists, which it exists when the left limit of the quotient equals the right limit of the quotient, whether we are using the original or the modified version, the alternate form of the definition of the derivative. And if the function is continuous and it is smooth with no vertical tangents, then you know the function is differentiable. Okay. Then we go to the intermediate value theorem. The intermediate value theorem was an existence theorem that pretty much said that if we knew that our function was continuous on a closed interval, and that we had some y value, some k, that was in between the y values of the endpoints, then there had to be at least one number c, which is an x value in your interval, such that when you plug that x value into the function, you would get the k. All right? So an existence theorem. What we're going to be looking at first in this first section, section 4.1, is the next existence theorem, which is called the extreme value theorem, which is pretty much fairly straightforward. Pretty much it's going to say that if we have a function that is continuous on a closed interval, so notice that the number 1 here and number 1 here are the same, but that's the only condition we need for the extreme value theorem. So if we have a continuous function on a closed interval, then we are guaranteed that there exists a global max and a global min in the interval. Could be more than one, but there must be at least one global max and one global min. All right? So keeping in mind that this is what we're basically talking about in this section, then let's do a little bit of a review of our extrema from pre-calc. Our absolute, also known as our global extrema, the absolutely the highest or the lowest point that's on the graph, that the y value, okay, now we do want to make sure that we keep up this idea that the y value is the global max and the location of the y value is the x value, okay? So f of c, the y value, is the global max if and only if, this IFF, the y value at this point is greater than or equal to the y values at all the rest of the points. In other words, what we're trying to say is that there is none higher. There are no higher y values. You could have y values that are at the same level, but there are no y values higher. There's none higher. And it's a global minimum if and only if this y value at c is going to be less than or equal to the y values for all the rest of the x's that are in your interval, that there are none lower. It's okay to have some that are at the same level, but they can't be any lower. All right. And that's kind of one of those things. It's like when you talk about like your sine graph, for example. In the sine graph, you would be tempted to say that there is not a global max or min because there's not one single highest point. But that's not what our definition of global max and global min says. It simply says it's a point for which there are none bigger or higher, and a minimum would be a point for which there are none lower than it. It doesn't matter that there are others at the same level. So like the sine graph would have absolute maxes at pi over 2 and every 2 pi. So pi over 2, 5 pi over 2, and so on. All right, so now we're taking a look at an example just to kind of remind ourselves of what's going on with this. And so in this example, what we want to do is we're looking at determine the extrema on the interval. And this is really, we're only talking about the global extrema right now. So we do have a closed interval, so we're going to have our domain, basically we're kind of assuming that there's no arrows here, that these are going to end here and here. And so if I were to look at this and I were to classify this as global extrema, scanning across we would see that the highest y value would occur at this point, and the lowest y value is going to occur over here at this endpoint. Okay, so now kind of how we would write this, kind of our idea, remember the y value is a location. So this y value, f of d, is a global max, and it's located at x equal to d. So the x value is the location, the y value is the global max. And then over here, our well actually pay attention to what my letters are. This function was g, so g of d is the global max, and g of a would be my global min. So g of a is the global min, and it's located at x equal to a. Right? So that's our idea. In pretty much we have a function. This function is continuous on our closed interval. Okay, g is continuous. A to f. That there are no holes, there's no jumps, there's no infinite discontinuities or oscillating discontinuities. Now, what we don't want to do is we don't want to get confused that this cusp here means it's not continuous. Remember, the cusp means it's not differentiable. That's not what this is looking at. This is simply saying if a function is continuous on the interval, there has to be a high point and a low point. That's what extreme value theorem is basically going to be saying for us. Kind of working ahead a little bit to what will come in later sections is remember that not only did we talk about absolute maxes and mins, we talked about local maxes and mins. Things that are maxes and mins only on a certain section of the graph. And so like if I was classifying this point right here, this would be considered to be a local max. This point right here would be a local min. This would also be a local max as well as a global one, because if you're a global max, clearly you're locally going to be a max as well. This would be a local min. And we'll talk more about those a little bit later. This section is going to focus on the absolute or the global maxes and mins. All right, so let's take a look at these, a few examples that we want to take a look at and kind of remind ourselves what's going on with this. So first thing we're going to do is for each of these we want to sketch them and then determine the extrema if they exist. And by extrema, we're talking about global extrema. Okay, so we want to graph this on the interval, so it might be important to maybe calculate the y values of our endpoints. We know what this function is. We know that the function is essentially a parabola that's been shifted up one. So when I calculate my endpoints, I'm going to put in my -1. -1 is going to give me 2. And then I'll put in my 2. 2 is going to give me 4 plus 1, 5. We know the vertex is going to be at 0, 1 because we just shifted it up 1. All right, so we'll do that and put a point. And then we have our negative 1, 2. And since that's the vertex, I also know I have 1, 2, and then I have 2, 1, 2, 3, 4, and 5. So essentially the picture that we're going to be looking at, our sketch, starts here, dips down, and then comes up here, our part of our parabola. And then we're identifying the extrema if they exist, so this is fairly straightforward. We have a global min down here at the vertex. So remember, our global min is the y value, okay, and this occurs at 0. So y equal to 1 is a global min located at x equal to 0. Okay, and then so that's our global min. And on this closed interval, because we're stopping it here and here, our global max is going to occur right here. So our global max is going to be 5, or I like to stress this, y equal to 5, and it's going to occur at x equal to 2. So the global max is y equal to 5 at x equal to 2. The actual value of the global max and the location of the global max. So fairly straightforward and easy. Now if I change this, so it's essentially going to be the same picture that I had. The only difference here is now I have an open interval instead of a closed interval. So if we take a look at this, and keeping in mind what our extreme value theorem that I mentioned to you earlier, the extreme value theorem said I had to be continuous on a closed interval. So now the only change to my graph is that we're going to have open, it'll still come down to here, and 2, 5 go up to here. So that's the only change on the graph. So now when I go to identify my extrema, I am still going to have y equal to 1. I'll just draw an arrow here and here. I'm still going to have y equal to 1 is going to be my global min, but there is going to be no global max. So notice that just that slight change of changing from a closed interval to an open interval then made it such that there is no global max. This is not a point, so that can't be a y value that is the highest y value, and we all know that you can't pick a point y value close to 5, like 4.9, because if you picked 4.9, I could pick 4.99, and we could go back and forth forever. There is no single highest point for which there are none higher. You name one, I can always name one higher. Right? Now let's take a look over here at this one. So again, pretty much the same function. The only difference is that at x equal to 0, we're changing the location of that. So let's kind of get our sketch in of this nice little piecewise function. So we still have our basic function, 1, 2, 3, 4, 5. Now we are including the endpoints. So go back to a closed circle here. We're going to come down, but now the actual y value at 0 is going to be 2. So it's going to kind of skip over, have a point here, and then continue up to the 5. Okay, so now we start identifying our extrema, and we do have a global max, okay, because we have that point right there. So we have our global max of y equal to 5 occurring at x equal to 2, so we have that. But then we get down here and we see that we have a problem, that because this point no longer exists, and notice now, what am I violating? I'm violating the fact that I have a closed interval, but it's not continuous on the closed interval. It's not continuous at x equal to 0. And so in this case now I have no global min. So again, going back to the extreme value theorem that I showed you earlier, you had to have continuity on a closed interval. Okay, here I had continuity on a closed interval. I had a global min and a global max. Here I had continuity, but I did not have a closed interval, and so there was no guarantee that I was going to have both. I ended up having one, a global min, but did not have a global max. Here I had a closed interval, but it was not continuous on the closed interval. I had a discontinuity here at x equal to 0, and again, I had a global max, but I did not have a global min, so there's no guarantee of having both. All right, so let's take a look at a slightly different example down here. Let's look at sine of x. So if we were graphing sine of x on 0 to 4 pi, and hopefully you can do that fairly quickly because it's nothing more than 2 periods of a sine graph. All right, so pi over 2, let's just go pi, 2 pi, 3 pi, and 4 pi. Go a max of 1, min of -1. And in our sine graph, we do have a closed interval, so I'm going to include intercept, max, intercept, min, intercept, and continue my sine graph pattern, and include the endpoints. Okay, and so here is the picture where we were talking about, is there a global min and a global max? Well, yes, there is. There's actually more than one in this case. I have a continuous function on a closed interval, and I do have at least one global max and global min. I actually have more than one. In this case, we would have a global max value of y equal to 1, and that's occurring at x equal to pi over 2 and x equal to 5 pi over 2. So we actually have two spots where we have this global max value. Notice you only have one global max value. It just happens in more than one spot. And then we have a global min value of y equal to -1, and that's occurring at x equal to 3 pi over 2 and 7 pi over 2. Okay, so again, we had a closed interval, that we were continuous on the closed interval. We are guaranteed by the extreme value theorem to have at least one global max and one global min. I had more than one, but that's okay. All right, if we take a look at E here, and this one's going to do some special cases. If I take a look at E, I am graphing y equals 2 minus 3x on the interval -1 to 2. So that's nothing more than a linear function. Again, because I have an interval, I might want to find my endpoints of my interval. So let's do that. F of x. If I put in -1, -1 is going to end up giving me 2 plus 3 or 5. If I put in 2, I'm going to end up with 2 minus 3 times 2, 2 minus 6, -4. So we have -1, 1, 2, 3, 4, 5. So we're here. And then 2, 1, 2, 3, 4. And that's enough to draw your line, right? Because we have 2 points. And it's closed, so I'm going to include those and then draw my line in. All right, and then say, well, what is my global max and my global min? Do I have one? You might be like, well, there's no dips or extrema. And I'm like, well, yes, there is. The global max value of y equal to 5 occurs at x equal to -1, and then the global min value of -4 occurs at x equal to 2. So what you see happening here is that if you have that closed interval, even if there are no hills and valleys, there's not a lot of increasing and decreasing switching going on in the function, you are still guaranteed to have at least one global max and global min, because it could happen at the endpoint. And so you can simply, by examination, hopefully you're starting to see how the extreme value theorem works. It's a fairly easy theorem overall. One more special case that we want to look at. Let's take a look at f of x equal to 3. And we're changed our interval. I don't know why, -2 to 4. But on this one, I'm not even going to bother to plug and get the points, because f of x equal to 3 is a constant. It's nothing more than a horizontal line, and it's closed. So I'm going to include my points, and everywhere it's going to have a value of 3. So it basically comes across here at 3 and looks like that. And then the question is, this is interesting, is there a point a global max, a y value for which there are none higher. And what is that global max value? Well, the max value is 3 because there's none higher than 3, but there's also none lower than 3. So in this problem, there are infinitely many global maxes and global mins, and they both have the same value. There is a global max of y equal to 3 for x, and because it's a whole infinite number of them, I'm going to say x element of -2 to 4. Every value of x in this interval is going to give me the global max value of 3. And there's a global min of y equal to 3 also, again, for x an element of -2 to 4. You can have infinitely many global maxes and mins, and you can actually have a point that is both a global max and a global min, and it occurs in this special case on a constant function. So basically, using these functions, what we've determined and kind of reviewed is that in order to guarantee a global max and a global min, the interval must be closed and the function must be continuous. Now, this doesn't mean that if I had an open interval and I had a non-continuous function, I could actually have both a global max and a global min. Like we saw in a couple of examples up here, I had one or the other. In this one, I had a global min. I just didn't end up with a global max. It is possible to have both a global min and a global max if it's not continuous or the interval's not closed. But what this says is that if the interval is closed and the function is continuous on that interval, then you must have at least one global max and one global min, that it must exist, another existence theorem. So we're going to add this to our list of very important theorems that we're going to know, okay? And again, here you have to also kind of know when to use EVT, because we're going to have all sorts of these theorems that are available to us, and we're going to have to know which theorem to apply and use in the situation. So in this one, if I saw this picture, could I use EVT on this? Absolutely. It's continuous and it's a closed interval. Continuous and a closed interval. It would work here. Continuous and a closed interval. EVT would be a proper choice if you were trying to show that there existed a global max and or a global min on this interval. Okay? If the hypotheses are not met, then there's no guarantee that you have a global max or min. You could have a global max, you could have a global min, you could have both, you could have neither, you could have one or the other. There's just no guarantee. And what we're going to be using these for is to basically prove that there exists a global max or a global min on a function that we're looking at. All right, so example 3 here, we're going to determine if the extreme value theorem applies, and if it is, then we're going to find the extrema, and if it doesn't, state why. And then we're also going to go ahead and say, well, does it happen to have them in the interval? All right, so we're going on the interval 0 to 2, and here clearly we would say EVT does not apply. So do not at any point try to invoke EVT to come to any conclusions about this. And even though EVT does not apply, we're not guaranteed a global max or global min, but we may have them, so let's see what we actually do have. In this section, looking from 0 to 2, I would say over here, you have a global min of y equal to 0 at x equal to 2. And then kind of scanning across, because this point up here is open, there would be no global max on this example. All right, we'll come over here to B. In B, EVT does not apply again. We don't have a closed interval because we have an asymptote here at 2. Or you could also kind of look at it as we're not continuous on the closed interval because the 2, there's no function value at 2. Can we still look and see whether we have a max or a min? Well, we actually have open on both sides here, and this appears to be the lowest location of a point. This actually has no global min and no global max. And don't tell me the global max is infinity. It has to be a single y value for which there are none higher. And infinity is not an actual number, it's a destination, so we would not choose that. All right, if we take a look at C, again, 0 to 2, notice that we are not continuous. We have a jump discontinuity here in the middle. So our EVT does not apply. However, could we still have a global max and a global min? Sure. The highest value on this is going to be over here. I don't have any scale over here, so we would say that f of 2 is a global max, occurs at x equal to 2. And we also have a global min over here. We would say f of 0 is a global min, which occurs at x equal to 0. So even though you don't actually have the y value, remember you can name the y value using your function notation. Over here in this last example, here's our 0 to 2. And again, another example, EVT does not apply. However, do we have a global max and a global min? Yes, we do. Over here. And again, I don't have any scale over here, so I would say f of 1/2 is the global max, and it occurs at x equal to 1/2. And then right here appears to be our global min, so f of 3/2 is the global min, and that occurs at x equal to 3/2. Right? So what we're basically seeing here in this example, and I'll zoom out just a little bit so that we can see all of them. What we're basically saying here is that even though EVT did not apply in any of these situations, you may have a global min but no global max. You could have neither. You could have both, as I did in these examples. You're just not guaranteed to have them. What will happen in our applications that we have coming up, the first thing that you do is you say, I want to determine or prove that I have a global max. So if I have a global max, I want to prove that I have a global max. The first thing I'm going to check is, does the EVT apply? Because if the EVT does apply, we will use that to prove that we have a global min or max. If EVT does not apply, then we may have to move on to another theorem or more strategies that will be coming down the pike later in Chapter 4. So remember, this is like the first stage of our applications that we're going to look at. And then again, just to remind you, that special case, simply because you might see this, is that does EVT apply to this on the interval? The answer is yes. I have a continuous function on a closed interval. And then find the extrema, we would have both a global min and max value of y equal to 5 for every x value in the interval -5 to 5. So we have infinitely many of them in that case. Okay, so let's take a break at this point, and then we'll come back and we'll talk about our strategies, our techniques for if we have the equation of the function and we don't have a picture, how would we actually do that?